Welcome back to this class. So we were discussing about the multiple choice questions of Allen on AC circuits. So far we have completed 57 questions. So let's move on. So next is 58. Let's start. A sinusoidal AC current flows through a resistor of resistance R. If the peak value of current is IP, then power dissipated is. So basically, it is a resistive circuit. So for a resistive circuit, so power is basically given by V times I, and we usually give this peak value of, so basically this power is I RMS into cos phi, and the value of cos phi is nothing but, if you look at the impedance triangle, so impedance triangle is basically given by this. So this angle is phi, phase difference between voltage and current. This is XL minus XC or XC minus XL depending on the nature of circuit. This is right angle. So this is resistance and this is impedance. So value of cos phi is basically R divided by Z. So as this circuit is purely resistive, this R and Z are same. So R divided by R. So for purely resistive circuit, cos phi power factor is 1. So this is nothing but VRMS IRMS. VRMS IRMS can be written as, so a peak current is given. So I want to write this IRMS. So I can, so VRMS IRMS multiplied by resistance. This is the value of VRMS multiplied by IRMS, and this cos phi is 1. Now I can write here. So this is basically IRMS square times R, and IRMS square is I peak square divided by 2 times R. So my power through the power dissipated in the circuit will be I square, where this I is peak value of current times R divided by 2. Next, 59. An AC circuit draws 5 ampere at 160 volt. The power consumption is 600 watt. Then the power factor is again the same formula, power 600. 600 is given by potential difference of 160 into current of 5 into power factor of cos phi. So from this I get cos phi equals to 600 divided by 800. So which is nothing but 0.75. So my power factor is 0.75. Straightforward example, which is not correct for average power. So average power, the formula for average power, so this is P average. P average is basically defined as VRMS times IRMS. VRMS times IRMS. So if you write in terms of only resistance, you get, suppose this is a purely resistive circuit or any kind of circuit, you can write this as VRMS. This current, if you express in terms of VRMS divided by impedance of the circuit, so you get basically VRMS square divided by impedance. You can write this formula in terms of current as well. So you can write this VRMS as IRMS times impedance Z, again IRMS. So तुम्हाला मिळणार आहे IRMS square times Z. Similarly, if you write VRMS and IRMS as peak value of current, so I can write V0 divided by √2 multiplied by I0 divided by √2, where these are peak values. So I get V0 I0 divided by 2. Or simply you can write VI. So the incorrect statement is option 3, where this power is given as VI, which is not the fact because there is a factor of 2 in the denominator here. Okay, next, moving on. 61. 61. In an AC circuit, inductance, capacitance, and resistance are connected. Effective voltage across inductance VL, capacitance VC, resistance VR. Total effective value of voltage is. We have seen this in last class, last lecture. We have already seen. Let me draw the phasor diagram here. This is your I. This is in phase potential difference across resistance. This is 90-degree leading. That's why it is inductance, and this is 90-degree lagging. This is your capacitance. So if VL is greater than VC, then you have net over here, which is equal to VL minus VC. And these are at right angle with R, VR. That's why your resultant V is given by V square equals to VR square plus into bracket VL minus VC bracket square. So which is in option number 3. Next, 62. In an AC circuit, V and I are given by. So the peak value of V naught I have given 100. Current I naught we have given 100. The omega value is the coefficient of time t is again 100, and the phase difference, if you see, phi is equal to pi by 3, but this is in milliamperes, this is in volt. So that phase difference phi is pi by 3, and basically what it indicates, current I leads V, because additional angle is in power dissipated by the circuit. So power dissipated by the circuit, we know P equals to V naught I naught divided by 2 times cos phi. So this is 100 into, this is 100 milliampere, that's why 10 raised to minus 3 divided by 2 into cos phi. So this is cos pi by 3. Pi by 3 is 60 degree. Cos 60 is half. Half means, so this value is basically 1 half. Half 4. 4 if you divide by this 4, so this 4 gets cancelled here. This 25. And this is 0.1. So you get 2.5 watt. You get the power of 2.5 watt. You have to just simply use the formula. Nothing else. Next. 63. For a series LCR circuit, the power loss at resonance, series LCR at resonance. So at resonance, this impedance becomes equal to R, because your XL and XC both are same, right? And we have already seen the power dissipated. Power dissipated is given by V RMS, I RMS, and cos phi. And at resonance, this phi, as it is now purely resistive circuit, this is 1. So this is nothing but V naught I naught divided by 2, because I can write this RMS in terms of peak value. And again, if you write this particular thing in terms of only current, you get I naught square times R divided by 2. And if you use this particular value, you can write this as I RMS square times R. So this is basically I square R. So there won't be any omega L, omega C factor, because at resonance, omega L and 1 upon omega C would be same. So it would be in terms of only resistance, because the power will be only dissipated across the resistance. So that's it. I RMS square times R. Next, 64. In an alternating circuit, applied voltage and flowing current E equals to E naught sine omega t. Power consumed in the circuit. If you look at the expression, so the phase difference between current and voltage is pi by 2. And current I leads potential difference P. And we know the formula cos phi. Power factor is cos phi. Cos phi, phase difference between V and I is pi by 2. So cos pi by 2 is 0. So as power factor is 0, your power consumed would be also 0. So power consumed will be 0. So if you look at purely inductive circuit or purely capacitive circuit, you know that the phase difference between V and I is pi by 2. That's why there is no power dissipated across purely inductive or purely capacitive circuit. It will be only dissipated across your resistance. Okay, next, 65. 65, in which of the following case power factor will be negligible? So the first one is asked as power factor. So let me draw the impedance diagram again. So this is our impedance triangle. This is right angle. This angle is phi, phase difference between V and I. This is XL minus XC. This is resistance. This is impedance. So power factor cos phi is equal to R divided by Z. R divided by Z. What is asked here? Inductance and resistance both high. So this is basically R divided by square root of R square plus XL minus XC bracket square. So inductance and capacitance both are high. Again, let me write the formula for this. Again, we are going to detailing. R square root of R square plus this is omega square L square minus 1 upon omega square C square bracket square. Sorry for this, not this. Okay, now it is correct. Now, the first option, inductance and resistance both high. If my inductance is high, this L value is high, then this square is high, then denominator is high. But simultaneously, if my resistance is also high, then I may get higher value of cos phi. So it is not the correct option. So what I should expect, R should be as low as possible and L should be as high as possible from this particular expression. So which is this option? Low resistance, high inductance, low resistance and high inductance. So low resistance, numerator would be less. This is low value. If this is high, then my denominator will increase. So by the both effect of numerator being less and denominator being high, I would get less power factor. So the third option is right. Next, 66. V given, phase difference given. So wattless power. Wattless power is what? So I'll write here peak V naught 100. So peak I naught is also 100. And the phase difference between V and I is pi by 6. And basically I is leading the I leads V. I leads V. I want a wattless power. So wattless power is what? So if you know, it's like power factor is actually power, it denotes the power dissipated out of total power available, right? So this basic formula is R upon Z. So Z is the total available power, out of which R is dissipated across the resistance and the remaining is not dissipated. The remaining is called wattless. So remaining is what? So remaining I can give it in terms of what? So remaining is basically for XL minus XC. So the formula for wattless power is V naught I naught divided by 2. So this is total power, of which if you multiply it by cos phi, you get a power dissipated across the resistance, which is watt power, and wattless, for wattless, you need sin phi. You need sin phi. So what you get here, 100 into 100 divided by 2 multiplied by sine of pi by 6. Sine pi by 6, this value is sine 30. Sine 30 is half. And if you multiply it by this particular expression over here, you get 2500 watt. So this is my wattless power, 2500 watt. Okay, so wattless, remember wattless is the one which is remaining from the total wire by subtracting the dissipated power across the resistance. Okay, moving on next. Let's move on to 67. Okay, 67. What is asked in 67? An AC supply gives 30 volt RMS, passes through 10 ohm resistance. Power dissipated in. So we know this formula, power dissipated. This is purely resistive circuit, so power factor cos phi is 1. So I can directly write formula V RMS square divided by R. So let me explain how it is coming. So this is V RMS I RMS cos phi. And for purely resistive circuits, cos phi is 1. So if I want to write in terms of voltage, I can write V RMS multiplied by V RMS divided by impedance. And for purely resistive, impedance is nothing but resistance. That's why we have come here, this formula. So RMS value is given 30 square divided by resistance is given 10. So I get 90 watt. So this answer is 90 watt. Next, 68. An inductor of inductance L and resistor of resistance R joined in series are connected to a source of frequency omega. Power dissipated in the circuit. Power dissipated in the circuit. Again, power dissipated in the circuit. If you look at the formula, you want the formula in terms of potential difference. There is no current involved. So let me write this in terms of potential difference. Okay, so let me write this V RMS I RMS times cos of phi. And now if you look at the impedance triangle again, so what is impedance triangle look like? Now you have only inductance. So this is basically omega, sorry, this is XL, which is equal to omega L. This is resistance, right angle. This angle is phi. This is Z. And your Z is the square root of R square plus XL square is omega square L square raised to half. All right, no problem. So let me write this. Now I want this in terms of RMS. So I don't want current. So I can write this current as V RMS divided by impedance Z multiplied by cos phi. Cos phi is R divided by Z. So what I get here? So basically I get here V RMS square times resistance divided by Z square, and Z square is R square plus omega square L square. So I get VRMS. So it is simply written as VE. So V square R divided by R square plus omega square L square. So this is the power dissipated in the circuit. You must know the impedance triangle. This is the basic impedance triangle and basic formula and power factors. That's it. Nothing apart from that. Okay. Next, 69. For a given circuit, the power factor is, in the given circuit, power factor is defined as, let me define it again. If you look at the circuit, there is only resistance and inductance. So power factor is R divided by Z cos phi. R, your R as usual. This Z is basically R square plus omega square L square raised to half. Raised to half. Okay, L is given, 50 hertz is given. So let me find first omega L. Omega frequency is given, so that is 2 pi into 50 hertz into inductance is given 3.5. 3.5. So 100. So I use value of pi to be 22 by 7 into 100 means this is 350. So if you solve this would be 50. So this would be 1100. So omega L is 1100. Your R is also 1100. So your Z, as these both are same, this implies your Z would be 1100 times root 2. 1110, because if you square both and take a square root, you'll get 1100. So this cos phi would be R. This is 1100 divided by Z, 1100 root 2. So you get the answer of 1 upon root 2. So this is the answer. Again, you have to simply use the formula. Next, 70. In purely capacitive circuit, average power dissipated in the circuit. Purely capacitive circuit, again, V RMS, I RMS, cos phi, and this cos phi is 0 since value of phi, phase difference between current and potential difference, pi by 2. Same with the inductive circuit. Next question, energy loss in pure capacitive, 0. Power dissipated in pure inductance, 0. Power factor of LR circuit, we have already seen here. Power factor of inductive circuit, cos phi R upon Z. Z is given by this particular formula. So this is also sorted. So next, move on. 74. 74 is what? In 74, if alternating current of RMS value A flows through resistance, then power loss in resistance. Again, power loss in resistance. V RMS, I RMS, cos phi. So for a purely resistive circuit, cos phi is 1. I don't want V RMS, so I can write this as I RMS times impedance. And for purely resistive, impedance is equal to R into I RMS. So this is basically I RMS square times R. So I RMS is given as A, so it will become A square times R. It is A square times R. Okay, next 75. Which of the following device in alternating current circuit provides maximum power? So we know maximum power factor. Again, if you look at the formula, power would be maximum for which this power factor is maximum. This is maximum for purely resistive circuit. Purely resistive circuit, because the value maximum value of cos phi is 1, and that is for purely resistive circuit. So only resistor, it will be maximum only for resistive circuit. Next, Next is interesting question 76. Okay, comparing the LC oscillations with the oscillations of spring block system. Spring block system, if you remember the derivation, this mass into acceleration plus spring force is equal to 0. So from this I get the differential equation. M, acceleration is d2x upon dt square, second derivative of displacement, plus k times x is equal to 0. This is the differential equation, spring mass system. This is spring mass system. Okay. So what is asked here, if you compare LC oscillations. So let me compare LC oscillations. So what is LC oscillations? So LC, I have current. So if you take this particular thing like this, if you have inductance over here, you have joined a capacitor over here. So whatever energy lost by capacitor is gained by inductor, and vice versa. So if your capacitor is charged, it will start discharging, and it will set up the current flowing through this inductance, and at the same time this current flowing through inductance will again recharge your capacitor. So if you look at this expression particularly, if you write the differential equation, so this EMF across this, so EMF across this plus EMF across this, as there is no cell connected or source connected, it will be 0. So EMF across inductance is L di by dt, L di by dt, plus across this is Q over C equal to 0. This is Q over C equal to 0. Now I know if I differentiate this particular expression again, so I will differentiate with respect to t. What I get? L is a constant. I get d2I over dt square plus 1 upon C constant. I get a dq over dt equal to derivative of 0 is 0. Now let me divide this. Let me divide this expression over this. Okay. So, okay, all right. So we have this differential equation set up here. Now, how this equation can be written? L d2I upon dt square plus 1 upon C, and dq by dt is nothing but the current equal to 0. So now if you compare this particular equation and this, so this represents LC oscillations. This differential equation represents LC oscillation. So if you compare, both are similar. Your X displacement is exactly similar to current in LC oscillations. Your inductance here, your mass is exactly similar to your inductance. The spring constant is exactly similar to reciprocal of your capacitance. So this is the analogy between spring mass system and LC oscillations. And what we are asked here, the quantity mk is similar to. So if you take a product of m and k of this would be equivalent to taking product of L and 1 over C. So this is equivalent to L by C. This is equivalent to L by C. So this is actually interesting that spring mass system and LC oscillations are exactly same. So you can compare undamped oscillation of spring mass system, forced oscillation of spring mass system with LC oscillations with or without source, something like that. So these are basically similar differential equations, and there is an analogy between them. Okay, all right. Next, we'll move on. Next is 77. 77. In an oscillating LC circuit, the maximum charge on the capacitor is Q. The charge on the capacitor when the energy stored equally between the electric and magnetic field. So maximum means what? So we know energy across capacitor is proportional to square of charge. So for maximum EC, maximum at that time, let me write some constant K times Q square. So when this energy is stored equally between electric and magnetic. So now energy has become equal to EC max times half, because it is equally stored in magnetic and electric field. So maximum, when it is maximum in capacitor, in magnetic, so EL inductance at the same time would be 0, right? So it will keep oscillating between inductance and capacitance. When capacitance energy is maximum, inductance energy is 0, and vice versa. Now it has become half, so I can write this EC would be some K times, let me denote now, Q1 square is equal to, this is K times Q square divided by 2. This K gets cancelled. So my Q1 at now is basically Q divided by root 2. So this is the thing. Now EC has reduced by factor 2. So Q square has to reduce by factor 2. So Q has to reduce by factor root 2. This means answer would be Q divided by root 2. This means answer would be Q divided by root 2. That is what is asked. Next, 78. A fully charged capacitor C with initial charge Q naught is connected to a coil of self-inductance L at time t equal to 0. The time at which energy is stored equally between electric and magnetic field. So what is asked here, energy of capacitance is equal to energy across inductance. And this happens, if you compare this again, differential equation, L d2I upon dt square plus 1 over C times I is equal to 0. LC oscillation. So if you compare, this is your M, this is your K, right? And our natural frequency omega square equals to K divided by M. So this is equal to K divided by M. So this is nothing but 1 upon C, K divided by M. So it would be 1 upon LC. 1 upon LC, and this is what we have derived, omega equal to 1 upon root LC for resonance, right? So this is natural frequency, and if your system is oscillating with the natural frequency, you call it as a resonance. This is what is this. So omega is equal to 1 upon LC. Now when these energies, so if you look at the graphs carefully, this energy will keep oscillating like, suppose if you have charged capacitor, so it will keep decreasing, energy will decrease. Again it will do in opposite direction. That let me draw this like this. Again it will charge to maximum. At the same time this is 0, so when this is decreasing, it will start increasing. It will increase. When it becomes 0, it will become maximum. So it will be maximum over here. So when it becomes negative, it will start decreasing. 0. So 0, maximum. Again it will start. When it becomes 0, it will become maximum. Again it will become maximum. It will become 0. So this is, let's say this graph is for EC and this graph is for EL. So when they become same, this is what is asked here. So this is total time period. So 0 tt. So this one cycle is completed. So this is t by 2, this is t by 4, and now when they become equal, this is t by 8. So this happens at a time t equals to time period upon 8. Time period upon 8. So from this we get a time period t equals to 2 pi divided by omega. 2 pi divided by omega. So this is 2 pi divided by, or this is divided by 1 over root LC. So this is equal to 2 pi root LC. So from this t by 8, I can write 2 pi root LC divided by 8. Nothing but pi root LC divided by 4. So this is the answer. So this energy across this EC and EL becomes same at time t by 8. Time period divided by 8. And you just have to find the time period. And we know the resonant frequency 1 upon root LC, angular frequency. Okay, that's it. Next, 79. a LC circuit is in a state of resonance if CL neglecting ohmic resonant natural frequency is asked. So natural frequency is given by F equals to 1 upon 2 pi root LC. So let me find this value 1 upon 2 pi square root of L value is given 0.25. This is 0.25 into 0.1 micro. 0.1 is micro is 10 raised to minus 7. 10 raised to minus 7. Okay. This is what to be found. All right. Okay. This I can return. So let me find the square root of this particular thing first. So this square root 0.25 into 10 raised to minus 7. I can write as, let me write as 25 into 10 raised to minus 9. 10 raised to minus 9. Again, I can write this as, see, 10 raised to minus 9. This is perfect square, but this is not perfect square. So I have to write this as 25 into 10 into 10 raised to minus 10. Now I can take a square root of this. So square root of this is 5 into square root of this 10 raised to minus 5 into square root of 10. I can approximately write as pi, because pi square is approximately equal to 10. So I can write as pi. So let me write again here now. 1 upon 2 pi into square root of this term is now 5 into 10 raised to minus 5 into pi. So 5 into 10, 5 into 2, 10. Pi into pi, pi square. Pi square is again 10. 10 into 10, 10 raised to 2. 10 raised to 2 into 10 raised to minus 5. 10 raised to minus 3. Numerator 10 raised to 3. This is approximately 10 raised to 3 hertz. So the option, nearest option is 1007 hertz. So your answer would be 1007 hertz. This is how we should find the approximate value. Okay, so last question for this exercise. 80. 60 microfarad capacitor is charged to 100 volt. This charged capacitor is connected across 1.5 millihenry coil so that LC oscillations occur. The maximum current in the coil is. So maximum current is given by what? So let me find the potential difference. So I have to find the value of XL or XC, and how would we find the maximum current flowing through circuit? Okay, just a minute. Okay, so LC oscillations occur means what? LC oscillations means system is well, basically it is in resonance. So LC oscillations means it is in resonance. So for resonance, so at LC oscillations, it implies it is under resonance condition. And in resonance, your XL would be equal to XC. This gives us omega should be equal to 1 upon root LC. So let me find the omega first. So 1 divided by square root of L. The value of L is given to be 1.5 milli 10 raised to minus 3 into value of C 60 microfarad, 60 into 10 raised to minus 6. So I can write this value as 1 upon 60 into 1.5. This is 1 upon square root of, this is 90 into 10 raised to minus 9. So I can again write this in terms of perfect squares. So it would be 900 into 10 raised to minus 10. So if I take a square root of this is 30 into 10 raised to minus 5. Now let me find either XL or XC. So XL is omega times CL. So this is omega 1 upon 30 into 10 raised to minus 5 into 1.5 into 10 raised to minus 3 millihenry. So I can write this as 150 into 10 raised to minus 5 divided by 30 into 10 raised to minus 5, which is equal to 5 ohm. Now my XL and XC both are same. So maximum current flowing through circuit, Imax, I am connected across 100 volt divided by this XL. This is 5. This would be 20 ampere. This is 20 ampere. So maximum current flowing through circuit would be 20 ampere. So far we have completed this exercise. So in the upcoming lecture, we'll see the previous year questions for the NEET based on this AC circuit.